We will check these three exercises. We will not solve the entire exercise, but we will just give you a little advice. Especially for the last one, for the 3.3, we will just like start like the solution. We will just explain how to write this in terms of the random variables of our models, and maybe the next session we will get into the details about the solution of this 3.3 exercise. But we will first check out the 3.1. It's about reinsurance, and the exercise asks us to obtain the analogous formulas for the reinsurer total risk SR and the total cost the insurance company should pay for stop loss non-proportional reinsurance. Okay, by the total cost, it is the premium that the insurance company has to pay to the reinsurance company. Okay, so we will see how to compute this. It's not very difficult. It's not. It's like tricky, but it's not really hard. So we will first we will remember first what was the reinsurance model. In the reinsurance, we just have that our random variable S, that remember is the total amount paid by the insurance company on a period of time. We will see as the sum of two random variables. One random variable is called SI, and this represents the amount that the insurance company will have to pay for the reclamations over one period of time. And the other random variable, the random variable SR, represents the amount that the reinsurance company will have to pay for the reclamations that the insurance company will have over that period. Okay, so in the case for the stop loss non-proportional reinsurance, this is like the general model, okay? But in particular for the stop loss non-proportional reinsurance, we have that the definition of the random variable SI is given by the minimum between the random variable S and a fixed amount tau. Okay, this tau is a fixed real number, positive real number, and it's like the maximum amount that the insurance company will pay over all the reclamations that we'll have over one period. Okay, it's like a deductible. Okay, not the deductible, but in the case that we are analyzing, that is how this random variable SR is going to be. It's very similar to a deductible, because you have already analyzed this with the professor. But but today we are going to analyze what happens with this random variable that in this model has to be defined by the maximum between the random variable S minus the value tau and 0. Okay, so more explicit, this new random variable is defined as the value that this other random variable S minus tau gives, but only when this maximum is equal to S minus tau. So that happens when S minus tau is a positive number, and that happens when S is greater than tau. Okay, strictly greater than tau, or it could be also greater or equal. Okay, but that is also in the other case considered, because in the other case, if the maximum is equal to 0, this random variable is going to take the value of 0, and that happens when S is less or equal than tau. Okay, so if the total amount for the reclamations of the insurance company exceeds tau, then the reinsurance company is going to pay the quantity that exceeds. Okay, because that was the reason that I said that it's more or less like a deductible, because the insurance company will have to pay the value of tau. Okay, the fixed value of tau, and the reinsurance company will have to pay the quantity that is exceeding. Okay, that the random variable S is exceeding over tau. That is this quantity. And in the case that the random variable s is less or equal than tau, then the reinsurance company will not pay anything. Okay, that's because in that case the value of this random variable is equal to 0. That's what it represents. Okay, so we in this case, for this exercise, we have to compute first the distribution function of this random variable SR, obviously in terms of the distribution function of the random variable S. Okay, and with that we have to compute the expected value of the random variable SR. Why the expected value? Because well, only considering like the actuarial mathematics course that you have taken, the risk premium, okay, only the risk premium that you may pay for an insurance, in this case a reinsurance, that is like the same logic, will be the expected value of the random variable that represents the amount that you will have to pay as the insurance company. But in this case, the reinsurance company is like an insurance company for the insurance company. So in this case, what would be only the risk premium, that is important, only the risk premium that the original insurance company will have to pay for the reinsurance company will have to be this value, okay, the expected value of the random variable that represents what the reinsurance company will have to pay. But this is only the risk premium, because of course in real life the real premium that the insurance company will have to pay will be greater than this, okay, because the reinsurance company also have to put administration costs, etc. Okay, but the only the risk premium that they will have to consider to then compute the real premium that the insurance company will pay to the reinsurance company, it will be this, okay, that this is like the important part, okay, in the theory. So this is like the goal, okay, we want to compute the value of this in terms, of course, of, I don't know, maybe in terms of the distribution function of R or of S or something like that, but this is like the goal, okay. And to do this, we may note first that this random variable SR is greater or equal than 0, okay? Because there are only two cases, okay? In this case, is equal to 0, and in this other case, is equal to S minus tau. But since in that case S is greater than tau, this would be a positive number, okay? Well, a positive random variable, but once we have observed it, it would be a positive number. So, in general, it is greater or equal than 0. And it's also important to note that it's not a continuous random variable in general, okay? Because it may have, and it will almost always have a positive probability to be equal to 0. Why? Because the probability for SR to be exactly equal to 0 would be the probability to be in this case, okay? And how can we compute that probability? We can compute it in terms of the S random variable. So this would be, when does this happens, that this maximum is equal to 0? Well, when S, the random variable S, is less or equal than tau. So then this probability would be the probability of S being less or equal than tau, and this by definition is the distribution function of the random variable S evaluated on the real number tau, okay? And now, if we consider a positive real number S, why a positive real number? Because this random variable will not have a probability in the negative numbers, and when this S is equal to 0, if we want to evaluate the distribution function in 0, this will be this value, okay? Because in the negative there is no probability, and in 0 is this exact probability, okay? So then the other case would be taking a real number, little x, a positive real number, and in that case, if we want to compute the distribution function of SR evaluated on that positive real number S, by definition it would be the probability for the random variable SR to be greater or equal than the real value little s. And we can compute this by, I don't know how to call it, it's something like total probability theorem, but not the conditional probability version, just like the intersection of events version. It's very easy to check out that this holds. Okay, we can compute the probability of this event, but intersected with this other event, and then the probability of the original event intersected with the complement of the other event that we were intersecting in the first step. Okay, that is like very easy to see that this has to be equal to this, and obviously we select an event, an extra event that is helpful. Okay, in this case we can calculate the probability for the random variable SR being less or equal than the value S, but at the same time that the random variable SR is greater than 0. Okay, and on the other hand, we will have to add the probability of the event that SR is less or equal than S, but when SR is less or equal than 0, that is the complement of this other event. Okay, and if we want to compute this probability, it is only the probability that the two events happens at the same time, and we can rewrite this as the probability for the random variable SR to be greater than 0 because of this event, but less or equal than the little s value because of this other event. Okay, and this other probability, we can notice that since we are assuming that little s is a positive value, the intersection of these events would only be this one. Why? Because if these events happen, then this event may happen. Okay, so when we have something like that, we can, well, if you see it like the definition of probability that you have already seen in probability 1, probability 2, this event as a set would be totally contained in this event, so then the probability of this intersection would be only this event because it's contained in this event. Okay, maybe there are other ways to justify this, but okay, this is like a theoretical way, and it's fine. Okay, but the important thing is that this whole probability has to be just the probability of the random variable SR being less or equal than 0. And and on the next step, with the left probability, we can just substitute what would be SR in the case when SR is greater than 0. That going to the definition of SR, it is only possible that this random variable is greater than 0 in this case, right? So in this case, the SR random variable, when it's positive, is also equal to S minus tau. So we can substitute this here. So we will have to compute the probability of the random variable S minus tau being greater than 0 and being less or equal than the little value s. And on the other hand, on the right probability, if we want to compute the probability of SR being less or equal than 0, it would be just the probability of SR being exactly equal to 0. Why? Because the random variable SR is greater or equal than 0 always, so there is no probability in the negative values. Okay, so the probability of this whole event is just this exact event. Okay, when the SR random variable is exactly equal to 0, it's the same probability, and we have already checked out this probability. Okay, this probability is equal to the distribution function of S evaluated in the value tau, and this probability we can in this inside of this probability we can sum on each term of in the equation the real number tau. So then it will cancel here in the middle. Okay, so we will get just the random variable s, and in the left side of the inequality we will have the value of tau plus 0, which is just tau, and then in the right side we will have the value little s plus tau. Okay, that is here, and then we can compute this probability in terms of the distribution function of S. And if we do that, we will have to get the distribution function of S evaluated on this number, that is S plus tau, minus the distribution function of S evaluated in this other number, okay, that is tau. So we will get this quantity, the distribution function of S evaluated in little s plus tau, minus the distribution function of S evaluated in tau, but we had already the same quantity, but adding, so they will cancel out, and we will get that in this case, when S is greater than 0, we will have just this expression, okay, the distribution function of the random variable S, but evaluated in S plus tau, okay. And we can also check that this expression, okay, this to be equal to this, it also holds when S is equal to 0. That is this little step that we have here, okay? Because if we get the distribution function of SR evaluated in 0, we get that this probability, and this probability is equal to this expression, okay? That would be the distribution function of S evaluated in 0 plus tau. So in general, we can write the distribution function of the random variable SR evaluated on any real number S, little s, to be equal to this expression. The distribution function of the random variable S evaluated on the real number little s plus tau, okay? But this only when the real number little s is greater or equal than 0. In other case, it would be equal to 0, this distribution function, okay? Okay, so we have this expression, but if we made a little graph or something, we might have these two functions, okay? Because we have the distribution function of the original random variable S, that, remember, is what the insurance company will have to pay to the insurance holders, okay? In one period, okay, the total amount of the reclamations that the insurance company will have to face. And this, well, you have already seen like the typical behavior that this distribution function has. That is something like this. It is in the negative values is equal to 0. Then exactly in 0, it gets a jump. Okay, the height of that jump is the probability for that random variable to be equal to 0. That is the probability that the insurance company will have to pay nothing. That in practice is a very little value, because we may always have to get a total positive amount of reclamation, but I wrote it here like too big, but it may be very small, okay, in practice, but okay. There is a jump here, and then, well, it depends also in the kind of the insurance, okay. It might be a very exotic insurance, and that it may have I don't know, like a very big probability to the company to not pay reclamation for that insurance. But above all the insurance that the insurance company have, it is almost impossible that they won't pay anything. But okay, we write it here, so we can draw it, okay. But the important thing is that there is like this curve, okay. It has this jump, and then it goes like asymptotically to 1, or maybe it at some point is equal to 1, we don't know, but in general we don't know. But what happens with this other distribution function? With this distribution function, what it's saying is that you may have like the same curve, but because you are only adding something in the argument of this function, okay? So the behavior of the curve will be almost the same, but what you are doing is that you are like taking this part that is from tau to infinity of the curve, and like starting from here, and then you take this distribution function and you take it to the value of 0, okay? It's just like a relocation, okay? But you do not locate this other part, because if you locate this other part, like you get it to the left side, you will have a positive probability for for negative values, and we do not want that. So that is the reason that you just like cut this part that is in the values greater than tau, and then you take that part to the zero value, okay? And but the behavior of the function is the same, okay? I tried to draw it like the same, so it's like it might not see like that, but I tried my best. So it's like the same behavior here in this red curve, okay? And the important thing of that is that if we want to compute, for example, the expectation of SR in terms of the expectation of, well, not necessarily the expectation of S, but in terms of the distribution function of S, for example, well, we can, since these random variables are non-negative random variables, we can compute the expectation function of these random variables. Well, for example, the expectation function of the random variable SR, like the area that is up, well, not up, that is above, I think it's above, above this curve, okay, this area would be the expectation, well, not this area, it's also going to go to infinity, but like this area would be the expectation of SR, but since this is like the same curve of this part, okay, of this green curve, but only in this part, it would also be the same area that would be over this other graph, but since this but starting in the tau, okay, not overall the positive real numbers, just for the real numbers that are strictly greater than tau, okay. So like, what is like the interpretation that this have, that for the reinsurance company, like the behavior of the random variable is the same that the original random variable has, that the original random variable S has, but only like relocated, like we have to relocate the values that the random variable for the insurance company has. But once we have relocated, is like the same behavior, but just for the values when the random variable S is greater than tau. And that has a lot of sense, because if you just had like this, well, not that, if you just rest like this constant tau, the behavior, the random behavior of this random variable will have to be the same, okay? But just it would be relocated, okay? Just the values that this new random variable S will take would be different, but the behavior will be the same. And of course, if we consider the other case, when the original random variable S is less than tau, in that case, the reinsurance company will have to pay nothing. Okay, so that is the reason that this distribution function of the random variable SR is very similar, not the same, but is very similar to the distribution function of the random variable S. And of course, the probability for the random variable S to be less than tau, that is the probability when the reinsurance company has to pay something. Well, that depends, okay? That depends on the value of tau, but typically, in our context, this would be like a very high probability. It can be the other way, but typically this would be a high probability. Okay, why? Because the idea of the reinsurance is to pay, well, that the reinsurance company will pay like only in the catastrophic events. Okay, it's not necessary to be that way, but it's like the typical idea. Okay, but okay, enough of the graph. Well, in the graph you can see that you can compute this same area that would be the expectation of SR in terms of the area of this above this green curve. But to be more specifically, we will have to check it out with integrals. That is not very hard. In terms of integrals, the expectation of SR, since SR is a a non-negative random variable can be calculated like the integral, the Riemann sense of integral, like the integral from 0 to infinity of the complement of the distribution function, okay, of 1 minus f of SR, the distribution function of SR, evaluated on S, and then differential of the value that we are evaluating the distribution function, okay, that in this case would be also little s. This is a formula that it holds for any type of random variable. It only has to be a non-negative random variable, okay? And then we can substitute the expression that we get for this. Oh, here is like a little mistake, sorry. No, sorry, it was right. It was right because the indicator function when we integrate from 0 to infinity is equal to 1. And then if we substitute just that expression, f of SR being evaluated on little s being equal to f of s evaluated on little s plus tau, we will have this integral, the same interval, but with the value, well, integrating the value 1 minus f of s, not f of SR, f of s evaluated on s plus tau. And then if we define this new variable, like t equal to this one, to little s plus tau, the differential of this new variable would be the same differential of the variable s. And if we make the change, we will just have to check out these limits. When s is equal to 0, t is equal to tau, so the inferior limit will be tau, and when s goes to infinity, t also goes to infinity, so the new limits will be from tau to infinity, and we will just have to integrate 1 minus f of s evaluated on the new variable t, differential of that that new variable t, okay? So that will be like the mathematical justification of what I have already said, okay, that we can compute this area in terms of this other area, okay. But okay, in integral terms, we will have that the expectation of the random variable SR would be equal to the integral from tau to infinity of this function, okay, of 1 minus f of s evaluated on t, okay, differential of t. Another formula that you can get, there are always like more than one way to get the answer. Another formula that you can get for this same value would be using a little trick that you have already seen with the professor, but I remember to you. You can remember that for any two real numbers a and b, the maximum between a and b, you can write it as a plus b plus the difference, the absolute value of the difference of a and b, okay? And then divided by 2. This is like a very nice property for the maximum. There is also a very similar property for the minimum, okay? But in this case, we will have to use the maximum. Why? Because we have this random variable SR defined in terms of a maximum. And what we can do is use this, and then the expectation value of SR would be the expectation value of the maximum between S minus tau and 0. And using this property, we will have that this maximum is equal to the first number, that is S minus tau, plus the second number, that is 0, plus the absolute value of the first number, S minus tau, minus the second number, that is 0, and then over 2. And simplifying and using the expectation properties, the linearity expectation properties, we will have just that this would be equal to 1/2 of the expectation of S plus the expectation of the absolute value of S minus tau, and then minus the value of tau, okay? This is also like I don't know how useful it can be, but it's also a formula that you can get in the theory. And maybe to compute this expectation value would be like, maybe it could be hard, maybe it is not hard, but okay, if you do not like this expression, you can also get this expression. And there is also another expression that you may have, but but we will check it out, and not in this exercise, but we will make something very similar in the next exercise, because the next exercise is very similar to this one. So now, in the next exercise, we will read it first. It says, for excess of loss reinsurance, obtain formulas for the expected value of the random variable YR, the variance of that random variable, the distribution function, and then the expected value of the random variable SR and the variance of the random variable SR. Okay, so we will of course remember what were that random variables defined by. Okay, and in that form of reinsurance, well, in general, also always in the reinsurance model, we have that S is equal to the sum of two other random variables, okay, SI and SR, okay? We have already explained that. But this type of reinsurance is for collective model, for a collective risk model, okay? If you have that the original random variable S is a collective risk model, that is something like this, no? Like the sum from j equal to 1 to a random variable n, okay, that the frequency random variable of some severity random variables. In this specific model that is called excess of loss, yes, excess of loss, you have that for each severity random variable, you define two random variables, okay, gr and gi, okay. Okay, to be more correct, we will have to use like the j here, but we will avoid this until it's really necessary to be like more clear with the symbols, okay. But in general, you do something like this, and this is right because remember that in the collective risk model, you assume that the severity random variables are independent and identically distributed. Okay, so we can write something like this. Okay, it is clear. I hope that is clear. And to be more specific, we define that this, for example, no, like the yi random variable, that would be that. What would this represent? It would represent the amount that the insurance company will pay, but for this specific severity, okay, for a specific severity. And the other random variable, the YR, would be the amount that the insurance company will pay for an specific severity, okay. But since there are identically distributed, it would be in general. But of course, no, for each severity, you will have different values that you will observe of the random of the distribution of the severity. So for each claim that you will have over the period, you will have to check out how was the value of this random variable, of the part that the reinsurance company has to pay, and how much was the part of that the insurance has to pay, and that you will have to do it for each of the claims. Okay, so and in this specific model, that is the excess of loss, you define that that the part that the insurance company will have to pay over any of the claims would be something very, very similar to the other model that we were using, that was the stop loss model. Okay, in that model, you had in general for the random variables of the total amount of the reclamations, you have like a maximum value tau that the insurance company will have to pay. Okay, this excess of loss is like the same idea, but for a collective risk model, specifically for a collective risk model, and instead of using a maximum amount for the total of the reclamations, you use a maximum amount that the insurance company will pay, but for each of the reclamations. not for the total amount of the reclamations. No, for each of the reclamations, you have defined a value of tau that will represent the maximum value that the insurance company will pay for one reclamation. Okay, and you do that for each of the n reclamations that you will have over the period. Okay, where n is obviously a random variable in this case. Okay, so that's the reason that this is defined like this. Okay, it's very similar. Now, the part of the reclamation that the insurance company will have to pay is the minimum over g and tau. If if over y and tau, if y is less than tau, the insurance company will have to pay everything because it is less than the amount that they have fixed. And if the claim exceeds tau, then the insurance company will only have to pay tau, and the rest will be paid by the reinsurance company. Okay, so in order to respect this, the only way to define the other random variable, you can check out the details, but it's very similar. Well, I believe that you have already checked out with the professor that these two random variables the sum is always equal to y. Okay, but if you do not have check out that details, you can do it. It's not very difficult. You can use, for example, these tricks. Okay, these tricks and the other tricks that is for the minimum, and using that tricks is very easy to check out that if you want this to happen, and you define that the random variable yi is equal to this, then the random variable yr, it has to be equal to this other expression. Okay, that is then in this case would be the maximum between y minus tau and 0. Okay, so yeah, it has sense. Okay, this says that the reinsurance company will pay y minus tau because well, in case when y is greater than tau, okay, that is when this is the maximum, and it is y minus tau because in that case the insurance company will pay the value of tau, so then y minus tau plus tau would be equal to y. Okay, and in the other case, when y is less than tau, this maximum would be 0, and then the reinsurance company will pay 0. Okay, and also it's very similar to the exercise 3.1. Okay, just that the difference is that in exercise 3.1, sorry, you fix the value tau for the total amounts of the reclamations, and in this case, in the excess of loss, you fix the total amount the maximum amount, that the company will pay, but for any of the reclamations. Okay, that is the difference. One is for the total amount of the reclamations, and one is for a specific reclamation. Okay, but that is like the concept. But in the mathematical model, it's very similar to get expressions for this random variable SR. In this case, that is what we are interested, and in this case, we will have to get the similar expressions, but for this random variable yr. So it would be very, very similar, and well, to be more specific, in this case, the real random variables that we are interested in that there are si and sr. Yeah, in this specific case, it would be the sum, from j equal to 1 to the random variable n, and the part of the insurance company would be to sum with these values of j, these random variables yj. Okay, but for a specific reclamation, so it would be the minimum between yj, that is for a specific reclamation, and tau. Okay, it's like this expression, but just like in the particular reclamation of the jade. Well, the jade reclamation, because this is not for the jade policy, because remember that in the collective risk model, you do not model each policy individual. You model the severity distribution of any of the reclamations. You do not care about which of the policy was that reclamation. Okay, and similar, no? If the part of the total amount that the reinsurance company will have to pay would be the sum of this new severity random variables. Okay, would be the sum from j equal to 1 to the value that reports our random variable n of these expressions. Okay, the maximum between yj minus tau and 0. Okay, sorry, I didn't say that. So and now if we want to compute expressions for this, for example, no, we have already in a very similar model, we compute the distribution function of a random variable that in that case was SR, that was defined very similar to the other exercise. Okay, and we also compute the expectation value of that random variable. So if you check out the details of how to compute the distribution function of the random variable yr and the expected value of the random variable yr, it would be very similar, almost identical to the computations that we have already did. Okay, but so I only say that, okay, it is very similar to the exercise, but of course, no, in this case, it would be the distribution function of the random variable yr evaluated in a real number y, and it would be f of y, the f of the severity distribution, okay, evaluated in y plus tau, okay, when y is greater or equal than 0, and of course the expectation value, the expected value, sorry, for this random variable yr, it would be also the integral from tau to infinity from y of 1 minus f, the distribution function of y evaluated in y dy, sorry, dj, I don't know, yj, I don't know if I am saying it right now, it's j. I have been saying y. Sorry for that. It is j. But okay, the important thing is that you can do the calculations by yourself. They are very similar to the last exercise. And in this case, we will, for example, it also asks for the variance of yr, for example. So to compute that, to compute that, you only have to watch this, okay, to get to note this. If you have the random variable yr but elevated to a number k, okay, this would be also just have two cases, okay. It would be the random variable yr that is y minus tau, but elevated to k when y is greater than tau. Okay, this is one of the cases. And the other case is when the random variable yr is equal to 0, but 0 elevated to k is equal to 0. Of course, if k is, I don't know, positive or something like that, okay, we will have to, we are not interested like in the 0 moment or something like that, okay. We are interested in to be specific, sorry, we are interested in positive integer moments, okay. So this will be 0, there is no problem. In the case when j is equal to less or equal than tau, and you can rewrite this as this expression, okay, but times the indicator function of this event, okay, because if this event holds, then this indicator function will get the value of 1. That this indicator function is also a random variable, okay. And if this indicator function is 0, is when this event is not happening, that it would be that this other event happens, and in that case this random variable will get the value of 0, okay. That is what we want, and using this, it is not very difficult to justify that the expectation value of the random variable jr elevated to the k is equal to the expectation value of this random variable, but conditional, the conditional expectation of this random variable, okay, j minus tau equal to, elevated to the k, but conditional when on that j is greater than tau, times the probability of that event. Okay, it's not difficult to justify this. Okay, because in the other case, the random variable is equal to 0, then the expectation is equal to 0. Okay, this is very easy to justify this. You can also check it out as a conditional expectation in terms of this random variable of the indicator function if you want to do it like very theoretically. But okay, there are a lot of ways to justify that this holds, and there are all the ways are very easy. Okay, you can write it down, and we are also interested in computing, for example, the expectation value, both of the random variable SR, and that is also like very straightforward. It's not very difficult. You just have to use a very similar method of what you have already done with the professor when you compute the formulas for the expected value of S and the expected value and the variance of S in a general collective risk model. What you have to do is to get the expected the conditional expected value of SR, but condition it on the event when the random variable n is equal to a specific value little n. And in that case, it's very easy to see that this conditional expectation of SR would be the sum from j equal to 1 to n, that would be substituting the random variable, okay, of the expectations of these random variables, okay, the random variable, the minimum between, of this random variable because we are computing the SR expectation, okay, so it would be the sum from j equal to 1 to little n in that case because we are conditioning on this, and of the expectation of these random variables, okay. And since they are identically distributed, since the yj are identically distributed, it is not very difficult to see that these other random variables, that would be the yr for example, would be also identically distributed. So this value would be always the same, and we are adding up that value n times. So we will have in general the expectation of any of that random variables, as we can call it the expectation of the severity of the new severity random variable that we called yr, jr, okay, and that would be multiplying to n, okay. And then if you want the conditional expectation of SR given the random variable n, it would be just to substitute little n for the random variable big N. And then if you want to compute the expectation of SR, you can do it like the expectation of this conditional expectation. So then the expectation of SR would be the expectation of N times the expectation of YR. And of course you can check out that, for example, since I didn't mention that, but since this integral is strictly less or equal than the integral when from 0 to infinity, like when tau is equal to 0, for example, that integral would be the expected value of y. So in general, this expected value of yr is less or equal than the expected value of y. And oh yes, it's y. I sorry for that. Sorry for my very bad English. And you can, it is only like a comment, okay? You can check out that this expected value, this new expected value, that is the expected value of the amount that the reinsurance company will have to pay in this model, it is less or equal that the expected value that the insurance company without insurance will have to pay. That this is like very obvious because the insurance company will not pay more than than the insurance company will have to pay without making the reinsurance. Okay. Also, it is valid for the insurance company that it will that the we expect that they won't have to pay like the same amount. They will have to pay a smaller amount, but it is also valid for the reinsurance company that they cannot pay more than that the value that the insurance company would have to originally pay. Okay, that makes sense. And of course, in practice, it would be strictly less. Okay, it won't be equal. Okay, but in general, we can just be sure of this. And with a very similar method, we can compute. Well, not with a very similar method. With this expression, okay, we can compute the variance of YR, and then with a very similar method of this one, you can compute the variance of SR. Okay, it's very similar of the calculations that you have already did. I repeat, when you compute when you get the formulas for the expected value and the variance of a random variable with this model, okay, with a collective risk model. Once again, sorry for my bad English, but okay. I will continue with the last one. It says this is a very interesting one. It says another kind of reinsurance is known as surplus proportional reinsurance, where the proportion of risk to be transferred might be different for each policy, since the insurance company wants to transfer the resulting proportion corresponding to the excess over a fixed amount for all policies. Obtain the analogous formulas for the types of reinsurance already analyzed during the course. Okay, so we have to obtain formulas for the expectation of S, for the variance of S, of course for SR, for SI, or the both the expectation and the variance, and if we are able to, maybe the formula for the distribution function of SR and the distribution function of SI, and well, that would be like the minimum values that we will be able to at least get a theoretical expression. Okay, but the difficult part of this exercise is not to do the computations. The difficult part of this exercise is to write what is saying here in terms of our random variables, okay? To define our random variables that we will have to use to then use the computations that we want, okay? So we will explain it, okay? This is a very strange reinsurance method, okay? It is useful, okay? It is used in the practice, but it's not like very common, but it is like very specific, okay? It is very tricky. So for each policy, well, first of all, it do not says like the explicit well, it do not say like the explicit sentence here, but the idea of this reinsurance method is intrinsically for an individual risk model. Why? Because the idea of this, I don't know. I'm not a fan of the way that the professor write it down, but when you talk about surplus reinsurance, surplus proportional reinsurance, you refer to something more or less like this. Okay, maybe you can find it out, write it in other terms, but if you want to write it out in terms of random variables, it is usually referred to something like this. The idea is that for each policy, okay, well, for the amount paid but for each policy, the amount of the claim for each policy, that we will call it XJ, we will have to get a maximum insured amount, okay, for each of the policies. So that maximum insured amount, we will just call it tau j. That would be a positive real number. Okay, and that is the reason that we need it to be with the individual risk model, because if you are in a collective risk model, you cannot have this. You cannot have that each individual policy has an a specific and a different, well, not necessarily different, but an a specific maximum insured amount. Okay, so if we have this, we have also to consider in this model that you have already decided a fixed amount tau that it is also a positive number, such that this happens. So this amount, well, it is like not necessary, but it's like when this model has like a little bit of sense. Okay, when this, we will see why. Okay, but this positive value tau, it has to be less or equal than all the other tau j values. Okay, so we can write it like the, oh no, sorry, well, we can write that this value of tau is less or equal than the minimum of all of each one of the tau j's. Okay, so if it's less or equal than the minimum, it's less or equal than every of the tau j's. Okay, from j equal to 1 to equal to n, because this is an individual risk model, so it has sense. We know the total number of claims. Sorry, not of claims, the total number of policies. And sorry, here is for the other size. This value of tau, it is also referred sometimes in some places, in some books or in some pages, as the retained line. It's like the number that retained line is the number that, sorry, not the number, is the name that they give to this number. Okay, and what does this number represent? This is like the because it says here. Okay, they want to transfer the resulting proportion corresponding to the excess over a fixed amount for all policies. So that value of tau is that fixed amount for all policies. Okay, and what it refers to transfer the resulting proportion. At least usually when you talk about this type of reinsurance, you defined that the proportion covered by the reinsurance for the J policy is given by this number. Okay, a number alpha j, that j is the number of the policy. Okay, that is equal to tau j minus tau over tau j. So what does this represent? This represents that you have a specific and a fixed value of tau that is called the retained line. Okay, and you check out for each of the policies how much the maximum insured amount, that is tau j, exceeds for that retained line. Okay, for that value of tau, you check out how much the maximum insured amount exceeds. That is the reason that this value of tau has to be less or equal than all the values of tau j's, because if we do not have this, then this could be negative, and that would not have sense, because this has to be a proportion. Okay, so first you have to check out by how much the maximum insured amount of a specific policy exceeds of the value of tau that you have already choose, and then you have to consider the proportion that represents that difference. Okay, how do you do that? Dividing by the amount of tau j, and it has to be by tau j, because this will change for another specific policy. Okay, for each policy you have to get a number between 0 and 1, because it would be a proportion, and it's like a very, I don't know, it's like a very strange idea. Okay, but it is used. Okay, it's not like the most used, of course, but it is used. So the idea is that it depends on how the maximum insured amount of a policy exceeds. uh, of that depends which proportion you will cover for that policy, for that specific policy. Okay, so you can do like the math and check out what happens if this value tau j is big, or what happens if this value tau j is little. No, you can check out that. Okay, but the idea is that, okay, you give for each individual policy a different proportion that is defined by this. Okay, the what is the proportion of the ex the of the value that exceeds the maximum insured amount for that policy over a fixed value that you have already choose. That I repeat, is called the retained line. Okay, so you do this operation for each of the policies, and then for each of the policies you get a different proportion. Okay, because typically the tau j is going to be different. Of course, if two policies have the same tau j, then this quantity will be the same, of course. But okay, in general, when you use the individual risk model, you have a lot of types of insurance that you are using. Okay, but and also, no, what this proportion represent? This represent the proportion covered by the reinsurance, no by the insured, sorry, by the reinsurance company. Okay, so if you want to write it in terms of the proportions that the insurance company will cover, you just take the complement and you can define another number, another set of numbers, bj's, that would be defined by bj's equal to 1 minus alpha j. Okay, it's not, it is equivalent to use it in terms of the proportion that the reinsurance company covers, of the proportion that the insurance company covers, but that is not important for the computations. And then for each of the policies, you will define this. Okay, this will represent the amount, the proportion, the amount of a specific policy and a specific policy J that the reinsurance company will cover. Okay, and that would be defined by this proportion alpha j times xj, and the other part of the payment that would have to be done would be the amount that the insurance company will cover for that specific policy, and it would be the other part. Okay, 1 minus alpha j times xj. Okay, well, remember, xj represents the amount paid by one specific policy. Okay, so remember, this is for and I didn't write it down, but this is for an individual risk model. Okay, and the real random variables that we are interested in, there would be SR would be the sum from j equal to 1 to n of alpha j times xj, and SI, the part of the total amounts that the insurance company will have to cover, that this is the real one that we are interested in, it would be the sum over j equal to 1 to n of bj equal times, xj. Okay, so I we have already do the definitions that you will have to use, but we won't be able to do the calculations because there are tricky ones. But maybe the next week we can get into the details of these calculations. The idea is that with these definitions, you will have to compute the expectation value of S, the expected value of S, the variance of SI, the expected value of SI, the variance of SI, probably the distribution function of SI, no, and also you may do the same, but for the other random variable, okay, for SR, no, and you can check that if this model of reinsurance really is like the expected value of SI gives you a smaller value than the expected value of S, etc. No, so it's not a very easy model to work with, because neither in the theory neither in the practice, because in the theory you will see that it's very tricky to manage. This is not very difficult, okay, but then to manage the sum of those random variables, it is very tricky to get a formula, or you get a formula that is not very explicit. And then for the for the practice, it is also very difficult to, well, not difficult, but it's not like very short to use this, because you have to compute this proportion for each of the policies, and typically you have a lot of policies, no, so it's not like the very like the most easy to use method, but it's also a method that is that is there, okay. And I know that maybe the text that the professor put in the homework, maybe it's not like very clear that it has to be something like this. I know that, but if you search out for the surplus proportional reinsurance, you you will find something very similar to this, okay. Maybe they won't write it down like in these exact terms, but the idea would be this one, okay.